This work approaches the challenging task of autonomous navigation in unknown tunnels with low-cost and consumable aerial platforms. In this work, a quadcopter is used to evaluate the proposed methods. The flight controller is ROS-Flight, and the Aeon upboard is the main processing unit. The operating system running on the board is Ubuntu Desktop 16.04, with ROS Kinetic also included. The main components of the proposed framework focus on the navigation, control, and vision capabilities of aerial platforms with low-cost sensor suites, contributing significantly towards real-life application. Generally, position estimation using visual sensors has the disadvantage of uncertainties and drift over time, due to the lack of prominent visual and geometric features in the general absence of illumination, making these approaches unreliable. While 3D LiDAR solutions for pose estimation would increase the cost of the platform, we present an architecture that considers the flying platform as a floating object moving along the tunnel, removing dependency on accurate position state estimation. To successfully navigate in a tunnel, the challenge for the MAV is to identify the direction of the flight in unknown areas, while avoiding collisions to the surrounding walls. In this work, two different approaches are proposed to define proper heading for the MAV. Initially, we demonstrate a navigation approach based on vector geometry using 2D LiDAR measurements to identify open spaces in the tunnel. Based on the knowledge that we fly in a tunnel environment, we consider the range with the largest magnitude to denote the open space in front of the platform. In this case, the range vectors that belong in the arc in front of the platform are added together into a vector sum. The vector sum will point closer to the ranges with the largest value, and therefore towards the open space. The difference between the vector sum angle and the current direction is used to generate a heading rate command to align the MAV direction with the open space. Subsequently, we demonstrate a machine learning navigation method using only the onboard camera stream to correct the heading of the MAV. The CNN receives a fixed size image as an input and provides 3 categories for each image. Similar to most neural networks, a CNN has an input layer, an output layer, and many hidden layers in between. For training the CNN, the setup consists of 3 mounted cameras with separated LED panels. Different cameras are used to reduce the dependency of training datasets. Additionally, datasets are collected with different illumination levels to consider uncertainties in illumination. Subsequently, we demonstrate a machine learning navigation method using only the onboard camera stream to correct the heading of the MAV. The CNN receives a fixed size image as an input and provides 3 categories for each image. Similar to most neural networks, a CNN has an input layer, an output layer, and many hidden layers in between. The method processes low-resolution and grayscale image streams to reduce the noise and computation time. These images are fed to a CNN designed to classify them into 3 categories: left, center, and right. This categorization results in preventing potential collisions into walls, while keeping the heading of the MAV towards the tunnel axis. This method can be applied independently to the type of the onboard camera. Moreover, the trained network can provide accurate classification to tunnel areas that have not been included in the training phase and shows robust performance with different levels of illumination, as can be seen in 2 videos from the onboard camera with different levels of illumination. Finally, the collected visual streams are post-processed offline with structure from motion techniques to provide a 3D surface of the visited areas.